Third skill, limits and continuity. So let's expand on our idea of limits for a moment and let's look at this graph. It says express the whole, which is right here, the vertical asymptote, which is here, and the horizontal asymptote, which are the endpoints or the end behavior of the graph as limits. So let's begin with our whole. Clearly we have a whole at x equals 2 and specifically at the point 2, 1. So one thing to keep in mind about limits is the limit exists so long as the left-hand limit and the right-hand limit are approaching the same value. And in this case, they're both approaching the value of 1. It's just we don't have a graph. Like the graph doesn't actually exist at 1, but the limit still exists. So we would say the limit as x approaches this value of 2 on the function as x gets closer and closer to 2, whether it's the left side or the right side, the limit equals 1. That's how we'll express our whole as a limit. As we get closer and closer to 2, whether it's from the left or the right, the limit exists. Becomes the limit is 1. Now, it would be wrong to say f of 2 equals 1 because that would mean it was closed here, but it's not. Right? F of 2 actually doesn't exist because there's a hole. If there was a dot up here, we'd say f of 2 equals 2. Or if it was up here, we'd say f of 2 equals 3. But keep in mind the distinction between the limit, which exists, and the value, which in this case does not exist. Let's try our vertical asymptote next. By the way, this is how we always write wholes, right? As x approaches the x value, the y value goes here. Okay, for our vertical asymptote, we have a vertical asymptote at x equals, let's call that negative 1.5. So at negative 1.5, on the left-hand side, the limit goes up towards positive infinity, right? As I get closer and closer to negative 1.5, my graph is going higher and higher and higher. But that's only from the left side. If I look at the graph from the right-hand side, which I'll do in green now, on the right-hand side of negative 1.5, let's say I'm like right there. Notice that the graph exists way down here, and as I approach it closer and closer, my graph continues to go down towards negative infinity. So my left-hand limit is positive infinity. My right-hand limit is negative infinity. Therefore, at vertical asymptotes, we never have, our limit will always be does not exist. Even if they were going the same way, actually, the limit would still be does not exist. So we would say the limit as x approaches negative 1.5 of our function doesn't exist. That indicates that we have a vertical asymptote. Now let's wrap up with our horizontal asymptote. We've discussed this already. Our vertical asymptote refers to the limits at the ends. So as x approaches infinity, notice that as you get further and further to the right, your graph is approaching the value of 2. In fact, that's also the same on the left side. As x approaches negative infinity, we're also approaching the value of 2. So we can write plus or minus infinity, just because they happen to be the same on both sides. So graphically, that's how we express these different features of a graph as limits. Let's try doing the same thing, but this time from an algebraic expression. So let's begin. F of x equals, let's factor. The numerator becomes x times x plus 3. The denominator is x minus 5. And immediately I see that I have a whole. Because that canceled, the root is 0, and that's where I have my whole. Okay, but it's not enough. It says write it as a limit. So limits, now limit expression says limit as x approaches 0 for our function. See what's missing? We don't know the y value. In the last problem, we were able to look at our graph and see the y value would have been 1. But here, we have to find the y value algebraically by plugging in 0 into our reduced expression. So if I plug in 0, I get 0 plus 3 over 0 minus 5, which is -3/5. And that's the y value that I have a hole at. If I were to graph this, it's at 0, -3/5. I don't know how the graph is behaving, but there's a hole there. And so that's part 1 of our answer. Let's move on and talk about part 2, our vertical asymptote. So vertical asymptotes are given by the roots of the denominator, because that's where the graph doesn't exist. You can't divide by 0. In this case, my vertical asymptote's at x equals +5. If I plugged in 5, I'd be dividing by 0. That wouldn't be okay. So let's write that as a limit. The limit as x approaches 5, for vertical asymptotes, we know the limits don't exist. So here's what's happening in my graph so far. I have a hole at 0, -3/5. At 5, I have some sort of an asymptote. Now the graph could be going like this, or it could be going like this, or it could even be going like this. It doesn't matter how the graph is behaving, the limit does not exist as x gets closer and closer to 5. Let's keep going. Horizontal asymptotes. As we've discussed before, the horizontal asymptotes are the limits as x approaches infinity. Since we have a polynomial expression, we know it'll be the same on the left and the right side. It's not like an e to the x as before, where it's different, left and the right. So let's observe. As x approaches positive and negative infinity, we're focused on the leading terms. Now, you might be wondering, should we look here at the original expression or at the reduced expression? It doesn't matter. It'll be the same. So notice in our original, we would get x squared over x squared once we get rid of the lower terms, which cancels to just 1, right? The leading coefficients are 1 and 1. If we looked at the reduced expression, we'd get x over x, which also becomes 1. So that's actually our answer. The limit as x approaches infinity of our function became equivalent essentially to the limit as x approaches infinity of x squared over x squared, which was 1. And we're done. Okay. Number 18 is now asking us to describe discontinuities. So it's important to know that there's 3 types of discontinuities. First, we have holes, which we've already discussed how to find. You're going to look for factors that cancel, and that'll tell you where your holes are. The second type of discontinuity is the vertical asymptote. Your graph can't continue, right? If you have to go over this vertical asymptote, it's going to become 2 separate pieces. And then the third type of discontinuity is a jump discontinuity, which looks like this. But this only happens with piecewise functions. So unless you're given a piecewise function, you're only looking for holes and vertical asymptotes. When I say piecewise, this only occurs with stuff that looks like this, right? Where the left-hand side can have a completely different function than the right-hand side. But since we're just given one single function, we're going to be on the lookout for holes and vertical asymptotes. As we said before, you'll have a hole where the factors canceled, so in this case at x is -5. You'll have vertical asymptotes at the roots of the remaining factors of the denominator, in this case at x equals 2. And this is what the graph would look like. Hole at -5, vertical asymptote over here at 2. Okay, that should give you like a visual of what's going on. So let's get into it. Let's factor, see what happens. Okay, it's already factored for me, which is great. So let's cross out. I immediately see I have a hole at x equals -4. And then what's left over shows I'm going to have two asymptotes because I have two roots in the denominator. My first root is at x equals 0. My second root is at x equals negative 2/3. So that's where my vertical asymptotes are at. Now let's look back at the question. It said, identify all the discontinuities. So we've done it. We've identified our discontinuities. Now we might want to use some elevated jargon, some elevated academic vocabulary here. So we'll call this a removable discontinuity, which is just a fancy way of saying we have a hole. And then for our vertical asymptote, we call that an infinite discontinuity. This is important in case you see these words. You should know what they're referring to. We're done. Let's try number 19. This time, you're going to try it yourself. So pause the video, identify all the values of x where the function is not continuous, aka identify the points of discontinuity. Go ahead, give it a shot. So after canceling x plus 3, one of the x plus 3 is on top, with the x plus 3 on the denominator, I'm left with this reduced function, which tells me that I had a hole at x equals negative 3, right, the root of that expression. And that leaves me with two vertical asymptotes, one at x equals 0 and the other at negative 4/3. These are all my discontinuities. I have a removable, I have an infinite discontinuity. Need two numbers that multiply to negative 3, add to negative 2. There'll be negative 3, positive 1. Check my math. So I have x minus 3 and x plus 1. Aha! Notice we have no cancellations. So there are no holes, but we do have two vertical asymptotes. We have a vertical asymptote at x equals 3 and another at x equals negative 1. And as we know, limits don't exist at vertical asymptotes. So we'd say the limit as x approaches a of our function does not exist for a equaling 3 and a equaling negative 1. Now try this one yourself. For what values does the limit not exist for this function? Pause the video, give it a shot. X minus 1 and 2x plus 1. So we have a hole at x equals 1, but no matter, we know the limit exists at holes. So that's not part of our answer. We want to know where the limit does not exist. So we're looking at our asymptotes are at 0 and negative 1/2. And let's use the variable they asked for, which was a. So the limit as x approaches a for our function does not exist for a equaling 0 and negative 1/2. All right, let's try 22 and 23. So sometimes you might see a question that says, define where the graph is actually continuous, which is literally just another way of saying, tell us the domain. Okay. So the domain of a function is where it's continuing to exist. The only things that we'll exclude are holes, right, because the limit's not continuous there. Jumps. The graph is not continuous there, as in you have to actually pick up your pencil, right? It's in different pieces. Or vertical asymptotes. So we're just looking for points of discontinuity, except instead of saying where it isn't continuous, we're going to say the opposite. So let's factor. Factoring always reveals important information. So in the denominator, I take out an x and left with 2x minus 1. Okay, no holes, but I do see a vertical asymptote at x equals 0 and an asymptote at positive 1/2. Well, that means that my graph will be continuous everywhere else. So the graph doesn't exist at these values, but it is continuous over negative infinity to 0. Then it We have to pick up our pencil at 0. Then we continue between 0 and 1/2. Then we pick up our pencil because of the vertical asymptote. And then we continue from 1/2 to infinity. So it's just another way of saying, hey, tell me the domain. Let's look at 23. It could have said find the interval of continuity, or it could have said find the domain. In either situation, since we're dealing with a radical expression, particularly an even root expression, we know we can't take square roots of negative numbers. So the inside expression, if you're finding the domain of root monkey, you'll always make sure that monkey is greater than or equal to 0. Because I can take the square root of 0, and I can take the square root of a positive number. The only thing I can't have under a square root is a negative. So to find the domain, let's set the inside guy greater than or equal to 0. So anytime I have a polynomial and an inequality like this, I know I'll be using the number line at some point. And in this case, I'll be highlighting where my graph is greater than 0, basically where it's positive or where it's equal to 0. Let's factor and see where our roots lie. Taking out an x, I'm left with 2x plus 3. Where is that greater than or equal to 0? Well, it's equal to 0 at 0. And it also equals 0 at -3/2. Sticking those onto our number line. Whoops, that's the wrong order. That's 0, that's -3/2. And then starting on the right side, we're positive in front. All of my degrees are odd, so I'm going to flip, flip. Now, I want to shade where I'm equal to 0, because that's allowed under the square root. And I also want to shade the positive numbers because it says greater than 0. So I'll be shading these outer extremities. Therefore, the domain of the function, right, where the guy under the square root is positive or equal to 0, is all numbers from -infinity to -3/2, inclusive, and then picking back up, including 0, and going to infinity. And that is our domain. Okay, we're approaching the end here. So, looking at number 24, now we're seeing our piecewise functions for the first time. It says find C such that f of x is continuous. Okay, so we know that for a function to be continuous, there can't be a jump. How do we check that there's no jump? The left-hand limit needs to equal the right-hand limit. That's very simply what we're looking for, right? The left-hand limit needs to equal the right-hand limit. Now, if the left-hand limit and the right-hand limit are the same, you'll for sure your limit will exist, but it doesn't mean you're continuous, right? Because you could have a hole. So to make sure we're also continuous, we make sure that there's no hole by saying, okay, the left-hand limit has to equal the right-hand limit, but that also has to equal the value. So that means that there's a plugged-in hole there. Now we're truly continuous. I want you to memorize this definition. Write it down. To be continuous, left-hand limit equals right-hand limit equals value. Another way of looking at that is right here. Limit as x approaches a from the negative side equals limit as x approaches a from the positive side. That's our left hand and our right hand limit, equals f of a, which is the value. So let's try that and see what happens. Okay, first, I'm showing my work. So left hand limit, I'm just writing the definition of continuity. Left hand limit equals right hand limit equals value. And also we want to make sure it's continuous, specifically at x equals 3, because that's the break point. So it says when x is not equal to 3, we're following this function. Well, if x is not equal to 3, that means you could be on the left of 3, you could be on the right of 3, you could be everything except for 3. So this is both my left-hand limit and my right-hand limit. And then it says if x equals 3, so that would be my value. So let's plug in 3 for x, everywhere we see an x, and then set them equal to each other. So we have c squared of 3 squared, or rather times 3 squared plus 1, that's the left-hand limit, right-hand limit side, equals the value. So when x is 3, we're left with c times 3 plus 3. The question is, find c, so that the limit equals the value. Let's continue. That's 9c squared plus 1 equals 3c plus 3. I have a quadratic. I'll keep my c squared positive, so I need numbers that multiply to negative 18 but add to negative 3. 6, negative 6 and 3, and I'm dividing by 9. That gives me negative 2/3 here and 1/3 here. So I get 3, reading bottom to top, I get 3c minus 2. And here, bottom to top, I get 3c plus 1 equals 0. So c can equal 2/3. C can also equal negative 1/3. And both of those values for c will make my left-hand limit equal my right-hand limit equal my value, meaning I have a continuous function. Okay, so there's a couple things that you just need to memorize if you're not going to be thinking of them intuitively. Like, this is very intuitive, but when it comes to the time of the AP exam, you don't have time to think through the logic of all this. So please memorize this rule and understand why it makes sense too. The limit exists if the left-hand limit equals the right-hand limit. But it's only continuous if the left-hand limit equals the right-hand limit and that value is plugged in. That's how you know you're a smooth curve with no breaks. So also know the definition of continuity. Left-hand limit equals right-hand limit equals value. All right, well, let's try number 25. Which definition are we interested in this time? Left-hand limit equals right-hand limit, or left-hand limit equals right-hand limit equals value? Which definition applies? Well, the question says, find A so that the limit exists. They didn't ask to make sure it's continuous. They just want to know that the limit exists. So we can be content with this less rigorous definition. We just need to make sure the left-hand limit equals the right-hand limit. So this side, it says x is less than 3. If this is 3, less than 3 is on this side, that's going to be the left-hand limit. This says x is greater than 3, so that would be the right-hand limit. Since it has an equal sign, we also would go here for the value. But as we know, the value is not relevant to this problem. We just want to know the limit exists. So write down left-hand limit equals right-hand limit. How do we write the left-hand limit? We say x approaches 3 on the negative side. That should equal the limit as x approaches 3 on the positive side for our function. So as x approaches 3 on the negative side, we'll be plugging in 3 into this function. It's for all the values that are less than 3. So let's plug it in. We get 2 natural log of a times 3 minus 1. That's the left-hand limit when x is approaching 3. On the right-hand side, we get to plug in 3 for x to this function, because this is the function that's relevant on the right of 3 for larger values. So let's plug it in. We get 2 times 3 squared minus 3. Now we need to solve for a. So we have 2 natural log. Let's just pretty this up a little bit. 2 natural log 3a minus 1 equals, that's 3 squared is 9 times 2 is 18. And 18 minus 3 is 15. We're solving for a. So let's move the 1 to the other side. Divide by 2 in the next step. And now we're stuck. We're in log form. We should go to exponential form. So cross out the log, write down the base. This is going to be e to the power of 8 equals 3a. I like to keep my variable on the left side, so I'll write e to the 8 on that, on the right. And I'm solving for a, so I'm just dividing. And I find that the a value that makes the left-hand limit equal the right-hand limit is e to the 8th over 3. And we are done. Okay, last problem of the day. Last problem of the day. I'm so excited. Says, find c so that the function is continuous. Okay, keyword, continuous. Why don't you pause the video, give it a shot, see how you do. Hint, there's 2 definitions that we went over. Only one of them applies here. So if you remember your definitions, continuity requires that the left-hand limit equals the right-hand limit equals the value. If we want to write this mathematically, then we need to say, which we do, then we need to say limit as x approaches, let's see. This time our possible breakpoint is at -1. By the way, notice that you're always plugging in to see at that potential breakpoint. That's what you're always using to plug in. So in the last problems it was 3, then it was 3 again. Now we're dealing with -1. So limit as x approaches -1 from the left, so that's minus, must equal the limit as x approaches -1 from the right, and that must equal the value at -1. We write that simply f of -1, right? The value when x is -1. Now, let's figure out what's our left-hand limit, what's our right-hand limit. If we're approaching -1 from the left side, then we want values that are less than -1. Well, that would be right here. This would be the left-hand limit because it's values that are not -1, so it's values to the left. It also is values that are to the right, right? It's everything except for -1, so it'll be both the left and it will be the right. And then for our value, we're looking here. It's where you equal to -1. Now let's plug it in and see what we get. Plugging in -1, recall we're always plugging that in for x. We'll get -1 times c plus 14. Now since our left and right hand limit are the same, we're just going to write that once, right? It doesn't make sense to write the exact same thing again. And we want it to equal the value at -1, so we'll plug in -1 here, because when x equals -1, we're dealing with this function. So it's 2 times -1 squared minus c squared. Let's see what happens next. -c plus 14 equals 2 minus c squared. Moving our c squared, whoops. What happened? Okay, moving our c squared to the left side so that it stays positive. We get c squared minus c, and I'm subtracting 2. It's going to be minus 12 equals 0. Let's factor. This factor is minus 4 plus 3. So I get c equals 4, and I get c equals -3. Those are the values of c that would make our function continuous, aka the left-hand limit equals the right-hand limit equals the value. And we're done, you guys. All right, you have a short homework assignment. See how it goes. Let me know if you have questions. All of the formulas and definitions that you need to succeed are provided in this video. So have fun.